Hello everyone, and welcome to the class. Partial differential equations done right. This is a sequel to my earlier course, ordinary differential equations done right. You can see I've recently updated the book. I will be updating it periodically as the semester goes on. But in this video, all I wanted to do was cover the foreword of the book for you. There's a few special things that I think we should talk about before we really jump into the PDEs. And that's the prerequisites, some of my notations, and how the book is structured. So we'll start with the prerequisites. It really needs a full calculus sequence as well as a course of ODEs beforehand, because you basically need at least 2 semesters of calculus before tackling ODEs, and if you want to get into systems of ODEs, then you're stuck taking Calc 3. Certainly for partial derivatives, you're stuck taking Calc 3 or some sort of multivariable calculus. And then ordinary differential equations, of course, is kind of the foundation for PDEs. A lot of times we're going to try to reduce PDEs into a large collection of ODEs. Now, this is always going to be an infinite collection unless we're trying to approximate it. But one way or the other, we're going to hopefully reduce PDEs into ODEs and then use some of our techniques from ODEs to solve them. So those are absolutely necessary. Something else that I want to comment on is the use of linear algebra. So you probably saw it in ordinary differential equations, the use of linear algebra, such as with the Wronskian matrix with variation of parameters. You probably covered a fundamental matrix or the matrix exponential when you're dealing with systems of ODEs. Similarly, when you took a multivariable calculus, you probably encountered the Jacobian matrix and its determinant, as well as dot products and linearization of vector fields. In addition to that, if you have taken linear algebra, some knowledge of the spectrum of a matrix, or thinking about eigenvalues and eigenvectors, or a change of basis formula, those will be useful for this course. I'm going to present some of my notation, because there's some notations that I will stick to. I'm going to try to keep them somewhat the same throughout, but they maybe are a little bit different than what you have experienced in previous courses. So we're just going to start with variables. 90% of my notation is with variables. So we're looking at t, s, and tau. I'm going to reserve these 3 variables for temporal variables in r+. So I use this notation r+, which I define as the right half plane, or the right half line. This is the real line, except we're starting at 0 inclusive and we're ending at positive infinity. Moreover, we're going to use the variables x, y, and z for spatial variables, and these are going to exist on the entire real line. In addition to all of that, we're going to sometimes subscript variables. Usually this will be with regards to spatial variables. And the idea is that we're going to be working in d-independent spatial dimensions sometimes. Sometimes I want to not restrict ourselves to 2 dimensions or 3 dimensions when we are doing some of these PDEs, and certainly with very large systems, we're going to have large dimension. So you could imagine in 26 dimensions, there are only 26 letters in the alphabet, and I don't want to go through A to Z and use those as my 26 dimensional variables. All of a sudden, I'm out of Roman variables, and I'd like to keep them around. So what I do instead is I'm going to subscript. So for example, in 26, I would subscript starting x1 and end up at x26, and those would be my 26 variables in a 26 dimensional space. This is also useful when we're subscripting if we decide we want to go into infinite dimensions, because in infinite dimensions, you just subscript by an I, and then you allow yourself to keep I going from, I guess I would go from like 1 to infinity. So that would be a situation in infinite dimensions where you subscript all the way up to infinity. It's also not uncommon for us to parameterize a spatial variable using a temporal variable. This would be the situation we say x is a function of t, y is a function of t, or z is a function of t. So they really are still spatial variables, but they've now been parameterized by time. This is the situation where if you have a point moving through space, you can say, okay, the point is a spatial variable, but it moves through space over time. So kind of the specific entry in the spatial variable changes over time. It's also not uncommon to parameterize a spatial variable off of a spatial variable. This is the situation in your earlier math courses, algebra through calculus, that you would be giving the y-axis, y actually is a function of x, or in Calc 3, the z-axis, where z is a function of x and y, right? Your third dimension sometimes was a function of the other 2. So this is not an uncommon thing to do, and we have to be a little bit clever sometimes, because a lot of times I may just use a z, I may just use a y or an x, and we have to be clever and realize that yes, z, x, and y, maybe they have dependence on another variable that we've introduced. This is very common with ODEs, right? We'll often write an ODE as y prime is y squared. That's a common nonlinear ODE, and you realize, okay, y is actually a function of t, because it doesn't make sense to take a derivative otherwise. Scalar fields are going to be represented by the Greek letters phi, or this variant on phi. I'm just going to call it var phi for variant of phi, and psi. So those are 3 maybe somewhat new Greek letters for all of you. Or F, G, and H in the Roman situation. So we may also use capital F or capital G in the Roman alphabet. A lot of times I'm going to keep these Greek letters, the phi, var, phi, and psi, as the unknowns we're going to solve in PDEs. And we're going to reserve the FGH or capital F and G. These are going to be known functions, but I'm trying to keep them general. So to make very general statements, we're going to pretend like, okay, F and G are known, but they haven't been determined for this particular theorem. That way, if somebody ever tells you to use the theorem when F is cosine plus sine, then you can just plug that in for F and you can actually get your result. But phi, psi, and var, phi would all still, they'd all be, unknown still in that situation. Partial derivatives have a few different ways of being notated. There's the true partial x that you probably saw in Calculus 3, and some people will use a subscript, phi sub x, to determine the partial derivative in the x direction. But I definitely like using the partial sub x of phi. This is my favorite way to notate a partial derivative. So the reason being, it still uses the partial symbol. In this one we've omitted the partial symbol. Still uses the partial symbol. It still tells you the direction that the partial derivative is taken in, but it doesn't take up quite as much space as the full partial x. So that's what I'm going to refer to with partial derivatives. If you don't remember exactly what partial derivatives are, all it is partial sub x of phi. This is going to be the limit, right? It's a limit, limit of a difference quotient. Delta x tends to 0 of phi. Suppose phi was a function of x, y, and z. We're just going to be looking at the difference quotient in the x direction. And then we're going to divide that by delta x. So it's just the difference quotient in the x direction. That's what a partial derivative is. You can get similar ones for y and z or whatever phi happens to be a function of. Now vectors in this book are going to be denoted by boldface variables. So here you can see I've used x, y, z, u, v, w, q, p. These are going to be common vectors for us. I don't use this over vector, the arrow that goes over a letter to denote vectors. That's a very common notation as well, but I kind of like this boldface to denote vectors. We'll also have vector valued functions. I'll try to use f's or g's for these, but I will boldface them, right? So if this is a vector valued function f, then I'm going to boldface it, which just means that the output of the function is a vector. The output is no longer a scalar. The vector x, we're going to use this vector x a lot, and that's going to be because I want a vector of all spatial variables. So the idea is, if we're sitting in R3 and we have 3 spatial variables, maybe we have a temporal variable too, but if we have 3 spatial variables, I'm going to group those together sometimes and just call it boldface x. That's going to be my vector of spatial variables. That's just going to be the vector x, y, and z. Furthermore, if we decide to give ourselves a lot of spatial variables, n dimensions maybe, I'm still just going to group them together into boldface x. So that's just going to be something that we should get used to. Boldface x will just be the vector of all of the spatial variables, no matter what they are. We have a boldface n here. Boldface n I'm going to try to reserve for one specific vector. This is going to be the outward unit normal vector. It's not going to take us long. It's in the second section of the book that we're going to encounter this object. But n is the letter n for normal, and it's boldface because it's a vector. It's not uncommon for other texts to use the Greek version of n, which is the letter nu. I know it looks like a V or a script V, but it's actually the Greek letter nu. So a lot of books may use this Greek letter nu to be the outward unit normal vector. So just be comfortable with either of them. There's a caveat on vector valued functions, right? So earlier I was talking about these vector valued functions, f and g, up top here. Those are vector valued because they're boldface, but in fact I will put one that's not in boldface. This is gamma, okay? And a lot of times I'm going to drop gamma's dependence upon t, but gamma is a very common letter used for parameterization of curves, right? Any sort of curve embedded in a space. You can think about a wire that I bend and I put it inside of a room, however the shape of the wire takes. If I were to put an ant on the wire and it walks around, that is the motion of the ant over time is a parameterized curve. So this is a common letter we use for parameterized curves, and I'm not going to modify it in this book. We just have to be okay with, okay, it's not boldface, but it is actually a vector valued object, or a higher dimensional valued object because it's embedded in a higher space. Our capital Greek letters phi and psi, capital phi and capital psi, these are kind of going to be catch-all. That's what I'm calling them for now. The reason for this is that we're going to be using these scalar fields, phi and psi, that I was saying earlier, and a lot of times those scalar fields will have some relational other functions. Something will be related to lowercase phi, and whatever that thing is I might call capital phi. But there are other situations where, well, capital phi is very common in the physics literature to be a tensor field, and the same as psi actually. Okay, so this is really common in quantum field theory. You would use capital phi and capital psi. So we may use them for tensor fields, and tensors are just higher dimensional matrices or higher dimensional vectors, and so on, and you'll encounter those in chapter 2. So we will use these for tensor fields sometimes, but we'll also use them for relationships with phi or psi. as the antiderivative or primitive sometimes of a phi and psi, and sometimes the lowercase phi or capital phi are both used as flow maps, and these will play a role in chapter 3, as you'll see. So you just have to be a little comfortable finding the context of phi or psi. I would say most often you should assume that they're going to be tensor fields, but you just never know. Matrices, I'm going to do my best to denote them by M. Okay, so capital M will be a matrix. If you see a capital M, just assume it's a matrix. I'll work really hard to say that this is not a matrix if you see capital M and it's not a matrix, but it is basically always a matrix. I'll use some other capital letters for matrices. Y is a common choice for the fundamental matrix of an ODE, just because lowercase y is often the vector that the fundamental matrix can induce if you acted on the initial condition. Boldface capital X is what I've often tended towards to a change of basis matrix. This is just because it's related to X, the spatial variable. So if I'm changing a spatial variable with a matrix, I'm going to use capital X. There's another Greek letter, omega. This is capital omega. This is going to be reserved for open connected subsets of RD or sometimes CD, but we'll basically be working in the real numbers in this course. And so there's this capital omega that is very common in the math literature, probably in the physics literature as well, to always describe an open connected subset. Maybe not always connected, but certainly always open. And then there's a thing called a boundary, which is related to omega. So when we take the boundary of omega, we're going to use the symbol partial omega, but I'm just going to call this the boundary of omega. And so this really does reuse the partial derivative symbol, but it's not a partial derivative. It's kind of related to a partial derivative, but I can't get into it in this course. There's some cool deep math going on with why this symbol is used, but we won't get into it. There's also the natural logarithm, which is a logarithm of base Euler's constant. I define this by log. A lot of mathematicians will end up defining this by log as well, especially when you get into higher level math, and not as ln, which is the common use of the natural logarithm. Just get used to that. I'll never use a log of any base other than e. Okay, so if you ever see a logarithm, it will be the natural logarithm. There's no point in ever using a different logarithm just because it's so easy to transfer between bases just by dividing. So we'll never use anything other than base e logarithm. So if you see log, it's going to be the base e log. There will periodically be other Roman or Greek letters. You should assume those to be constant scalars, unless in boldface, I'll use A or B, C, etc. But if they're in boldface, they should be assumed to be constant vectors, and then if neither of those are true, I will note otherwise. I will tell you what a variable is representing if it's not a constant. Finally, we'll cover the overall structure of the book. So in part 1, I call part 1 the introduction to PDEs, we're really covering preliminaries. So we're going to introduce PDEs, we're not going to solve any of them yet. We're introducing them, we're introducing domains, boundaries, some higher dimensional Taylor series, Fourier transform. We're getting ourselves ready. We're collecting the toolbox that we're then going to use in future parts, right? So part 1 is kind of a collection of tools. How do we use tools? Maybe getting used to them. But in part 2, we're actually going to use the tools specifically on PDEs. Okay, so we're going to see how to construct explicit solutions to some PDEs. We're going to pull this off with the method of characteristics for first order PDEs, and this first order PDEs are allowed to keep them nonlinear, which is very cool, but with second order PDEs we're forced to go straight to linear. Okay, so first order we have some nice tools, method of characteristics, that can be nonlinear, but second order we have to restrict ourselves to linear. Things get a little bit too tricky when we try to do nonlinear PDEs. In part 3, I'm calling this part spectral numerical analysis. We're going to study some integral transforms, eigenvalues and eigenvectors, really eigenfunctions, the spectral theorem, Green's functions, and finish with the Cauchy-Kovalevskaya theorem. This is a theorem where we can start to handle some higher order nonlinear problems, but it's not the best at producing closed form solutions. It's really similar to the power series method maybe that you encountered in ODEs. So think about Cauchy-Kovalevskaya as the power series method for PDEs, which is why we're doing the Taylor series in part 1. And then finally, we're going to talk about the finite difference method and Galerkin method for approximating PDEs. But anyway, that's all I've got for the foreword. I will see you when we get to section 1.1. Bye.